Hello and welcome to a new video on cryptography for everybody. In today's video, we will have a look at the Columnar Transposition Cipher. As you may remember, when you are a viewer of this or a regular viewer of this channel, that we already had a video about the Columnar Transposition Cipher. And actually this was one of my first videos that I made for this channel over 2 years ago. And today I thought it's a good idea to create a new video about that topic. Why? We recently updated the transposition analyzer in Crypto2 that is now more user-friendly and more easy to analyze transposition ciphers or columnar transposition ciphers. Therefore, in this video, we will have a look at the columnar transposition cipher and at its script analysis. We structured this video into 4 different parts. In the first part, we will have a look at the basics of transposition ciphers. Then we will have a look at details of the columnar transposition cipher, followed by the crypt analysis of the columnar transposition cipher. And finally, we will do it in Crypto2. We will encrypt and decrypt using the columnar transposition cipher, and we will break the columnar transposition cipher. What are transposition ciphers? Transposition ciphers transpose letters or change the order of letters to generate the ciphertext, in contrast to substitution ciphers, which substitute, so replace letters with other letters and symbols. We already had plenty videos about substitution ciphers on this channel, so if you are interested in learning more about substitution ciphers, just search for substitution. What does it mean that transposition cipher transposes letters? It means that the unigram letter frequencies, so the frequency of A, B, C, and so on, of transposed text are the same as the frequencies of the original plaintext. Since we do not change any of the letters, this is of course easy to see. But higher order letter frequencies, for instance 2 grams, 3 grams and so on, are different. That is because the ordering of our letters changes. So when our text starts with the, we have a bigram th and a bigram he. But when we transpose the text, then the word the is broken into different parts, and so we don't have anymore the first bigram th and the second bigram he, because the letters are in completely different positions. But as I said, the unigram letter frequencies of course stay the same, since we do not change the letters themselves. And transposition ciphers were quite difficult to use and therefore not used as often as substitution ciphers in history. But there are a few example usages in history. The first example is the turning grill cipher that was used, for instance, by Sir Francis Walsingham in the 16th century. And here you can see an example for a grill grid where you have some letters, a hidden message here inside, and you have other letters that are null letters so that the message is hidden here. Usually a grill was also created with holes. We already had a video about grill ciphers on this channel, and you had holes in the grill, and then you wrote the plaintext into the holes, then you turned the grill, that is called a turning grill, and the holes were at other places, and then you wrote the second part of the message and so on, and so your plaintext was transposed using the grill. Our second example here is the columnar transposition cipher, and the columnar transposition cipher is also part or the main part of this video, and it was used, for instance, in World War I and World War II as a hand cipher. Then our final example is the so-called double columnar transposition cipher, which was a very, very secure hand cipher in its time, and it was, for instance, used during the Cold War by Günther Guillaume. Here we have an example of a transposition cipher. We have a plaintext here in cryptography, a transposition cipher, and so on. This here is from the Wikipedia, from the English Wikipedia, just an example text. And this has been encrypted using the columnar transposition cipher, but we could have used any other cipher that transposes a text. And here on the right side, you can see the unigram frequencies and the bigram frequencies. And since the unigram frequency does not change, so this text here has the same unigram's frequency as this text here, we only need to have it once here. And as we can see, of course, T and E are very frequent letters here. This is because this is English here. And here we have the bigram frequencies of the plaintext. And the most frequent bigrams are, for instance, HE, TE, ON, TH. That are the most frequent bigrams also in the English language, and clearly in this English plaintext here, these are also the most frequent bigrams. But after using a transposition cipher, the bigram frequencies are changed. For instance, now here in this text, the most frequent bigram is TT, then AE, TR, IR, EN, and so on. So a complete different picture compared to the original bigram frequencies. And trigram and 4gram and 5gram frequencies are also different. And that's what transposition ciphers do. They do not change the unigram frequencies, but they change bigram frequencies and so on. Now that we know what transposition ciphers are, let's have a look in detail at the columnar transposition cipher. And the columnar transposition cipher got this name because it works on columns. That's why it's called the columnar transposition cipher. But you could also perform the transposition on rows of the text. The columnar transposition cipher transposes text, as each transposition cipher does, and it does this based on a keyword that defines the number of columns and the order. Here you can see an example, and you have here the keyword keyword, and the order of the transposition is defined by this keyword. How this works, we will see later. So how do you encrypt using the columnar transposition cipher? You first create such a grid here, and you write the keyword above the columns. And you write the alphabetical order of all letters on top of each letter. So we start with a D, then we have the E, then we have the K, and so on. And if a letter appears twice, the first letter gets the first number, and the second letter that has the same gets the next number. Then the columns are reordered based on the alphabetical order of the keyword's letter. So we have here the first column is now the column with the 1, the D column. Then we have the E column, which is 2, the K column, which is 3, and so on. And I marked the columns with a color that you can see where each color went to. Then in the final step, step 3, the ciphertext is read out column-wise. So you read this column here and write this into the ciphertext. The second column here, the third column here, and this here then is our ciphertext. And decryption is the reverse process. In the decryption case, you first order your keyword like this here, and then you have to mark, you have to know which are the shorter columns here, but you can compute this. Then you put here, you cross these out, or you make these black like here, and then you can start writing your text into the columns here. And when you transpose these back, you can read the original plaintext. Now we have to look in more detail at the columnar transposition cipher, because there are two types of columnar transposition ciphers. We distinguish between the complete columnar transposition and an incomplete columnar transposition. What does this mean? Complete means there are no empty cells in our last row. And this means that the length of the ciphertext modulo the length of the keyword is 0. You can see this here. When we put our text into this grid here, then we fill it completely. This is why we call this a complete columnar transposition cipher. And then we have the incomplete columnar transposition cipher, and here a minimum of 1 empty cell is in the last row. And that means that the length of the ciphertext modulo the length of the keyword is greater or equal to 1. As you can see here on the right side, the last 4 cells here, or the last 4 letters, are left empty, and that is why we call this an incomplete columnar transposition. And the most difficult incomplete case for cryptanalysis is when the last row is filled by half. That means that the length of the last row equals to the length of the keyword divided by 2. This makes this cipher more difficult to break. In this case, when you have a complete columnar transposition cipher and you do this by hand, you could just cut it into these strips here, and then you can just try to reorder the strips. But with an incomplete columnar transposition cipher, we have the problem that you have different length of columns, so it's not so easy to cut the ciphertext into these strips because you don't know where a column starts and where a column ends, making cryptanalysis more challenging. In this case, where the last column, the last row is only filled by half, the most difficult case. Now let's have a look at the cryptanalysis of the Columnar Transposition Cipher. And first, of course, we have a look at the key space size. And the key space of a columnar transposition cipher is the number of permutations of the keyword or of the columns. And with a keyword of length n, the key space size is n factorial. And here are some examples. Why is it n factorial? For the first element you have n choices, for the second you have n minus 1, for the third row column you have n minus 2, then n minus 3 and so on, and this is n factorial. Now let's have a look at some examples. For instance, with a key length of 15, our key space size is already 2 to the power of 41. This can still be searched through with a computer. But when we have very long keys like 25 or 50, we already have 2 to the power of 84 key space size, or even 2 to the power of 215 key space size. And these are very, very difficult cases. Now let's have a look how we can break a columnar transposition cipher. To break a columnar transposition cipher by hand, one has to, very simplified, first determine the length of the used keyword. We have methods to do so. And then we have to reverse the order of the columns. For instance, using bigrams, trigrams, aligning strips of paper and so on. So very tedious work, but you can do this still by hand. But in this video, of course, we don't perform cryptanalysis by hand. We use a computer with Crypto2 for doing that. And in Crypto2, we have 4 different attacks implemented in our so-called transposition analyzer. And later we will have a look at this. The first attack is a brute force attack that just tests every possible key. It's suitable up to a key length of 10, which takes about 15 minutes on a standard PC. And with key length of 12, we already have to wait about a day to search through the complete key space. Then we have a genetic attack. We already had videos about genetic attacks. And genetic attacks in Crypto2 for the columnar transposition cipher are suitable for larger key length. For instance, about 20 to 25. Same is with hill climbing. It's also suitable for very large keys. We already had also a video about hill climbing on this channel if you're interested how these attacks work. And this is the most powerful attack in Crypto2 on the columnar transposition cipher. And finally, we have the so-called crypt search. And the crypt search needs a part of known plaintext that we call the crypt. And this can then reverse the key using this crypt. Now that we know how a columnar transposition cipher works and which kind of attacks we have implemented in Crypto2, I want to go to Crypto2 and first encrypt and decrypt with the columnar transposition cipher component in Crypto2. And then I want to break some columnar transposition ciphers using the transposition analyzer. So let's go to Crypto2. I'm here now in Crypto2. And I use the nightly build 9273.1, so you need at least or at minimum this version if you want to do the same that I do in this video. And I want to show you at first how you can encrypt and decrypt using the columnar transposition cipher. For that I search for transposition in our template section in the Start Center, and then we have a template called Transposition Cipher. I double click this and we get this nice template here. We have to first define a key, and I want to have the key secret key. And then we want to have a test text, and let's write a text. So here we have a text with a secret key, and here we have 2 transposition components. The first component will encrypt the text. Let's have a look at the settings. So it will read in the text by row, then permutate the text by column and read out the text by column. Then we will see the encrypted text here, the ciphertext. This will also go into the second transposition cipher, which is set to, of course, the same modes here, read in by row, permutation by column, read out by column, but this is set to decryption, so it does this in the reversed order for decryption. And then we will see our plaintext here again. And let's now see how this works. Let's press play. And then we see here this nice visualization. We can slow it down a little. when it's in the permutating step. So it now read in all of our columns. Let's speed it up a little. This was the last. And now it transposes the columns that we have the alphabetical order here on the top. So we have here 1, 2, 3, 4, 5, 6, 7, 8, 9. And then it writes out our ciphertext. So we will increase the speed a little here. And this component was written by some fellow students when I did my bachelor at the University of Duisburg-Essen. And I think this is really nice. Here, this is the reverse order of the transposition cipher. It does everything but in the reversed order. And here we can see again our plain text. I think this is really nice. Let's speed it up a little. The transposition component is one example of very nice presentation, or it has a very nice, it's a component with a very nice presentation, I think. And here we have our original text. This is a test text which shows and so on and so forth. Now let's stop this and we copy our text. I hope it is long enough for the cryptanalysis. And we go back to the start center. And we still have here the results for the search for transposition. And first I want to show you the brute force analysis. You post in or paste in your ciphertext here. Then you have the transposition analyzer. And in the transposition analyzer, you can select which types of transposition you want to analyze. You can define the minimum key length. This is new. In the old version, you had to specify one key length. And I thought it's so annoying that when you want to test different key length that you have to stop and start and stop and start. So I added minimum and maximum key length. Now let's press play. And as you can see here, in about 30 seconds, all possible transposition ciphers are tested here up to a key length of 9. It's currently searching through 9. And here we have, this is a test text which shows how the columnar transposition cipher and so on and so forth. So we searched through all possible transposition ciphers or columnar transposition ciphers of key length 9, 8, 7, 6, 5, 4, 3, 2, and 1. No, of 1 makes no sense. This is no transposition. That's why we only can start at 2. So we broke the transposition using brute force. So how does this work? It tests all possible keys internally. It goes through all possible keys, and then it uses a cost function here, an n grams log2 cost function, and we used 5 grams to do so. And we selected use space. We could have deselected this because we have no spaces in our text. And I think spaces in transposition ciphers, this works in Crypto2, but makes not very much sense since you would never transpose a space symbol. You would probably remove the spaces as I did here, or you would replace the space maybe by an X or something else. Now let's have a look at another attack. I copy my ciphertext here, go back to the start center, and I want to have a look at the geometric analysis. This looks nearly the same. Of course, it's the same component. I paste the ciphertext here, but this time the transposition analyzer is set to a genetic algorithm. And it's already set to key length of 9 to 9. I think I will keep this. We know we have a key length of 9. If you don't know the key length, you could let it run for different key length, but let's just let it run with key length of 9. And yeah, this was really fast. So here's the solution. As you can see, it took about 1 to 2 seconds or 3 seconds and we had the solution already. Let's for fun start or test from key length 2 and let's see how long this takes. Okay, this takes about a minute. Okay, I will start with key length. Let's start with 7. Now it's 20 seconds. We have key length 7 here. By the way, when you double click here, you get the full screen view of the analyzer and you can close it here. We are now at key length 8. Now we are at key length 9 and it already found the original key. So the genetic attack is very powerful. And if you want to know how this genetic attack works in detail, I already also made a video about genetic attacks for cryptanalyzing historical ciphers and classic ciphers. Then have a look at that video on my channel. Finally, let's have a look at the hill climbing analysis. We also paste our ciphertext in here. Let's have a look at the transposition analyzer. We have hill climbing here. Minimum key length of 25 is way too much. Let's test from 8 or 7 to 9. And repetitions and iterations is fine. Iterations is the number of steps in the hill climbing process, and repetitions is the number of times the hill climbing should be restarted. Now let's have a look. Also 30 seconds, around 24 seconds. We are at key length 7 now. Here you can see how many keys my computer performs per second. So I have about 50,000 keys that are tested per second using hill climbing. Now we are at 9. Let's see if it can also find the solution. And hill climbing somehow fails. Sometimes when it doesn't work, you can stop it, but we know it's 9. Let's increase the number of repetitions to 50. If it still fails. I know, I'm stupid. In this template for the hill climbing analysis, the mode of the transposition cipher is wrong. So not wrong, but different. We read in by row, we permutate by column, but we also read out by column. I forgot to change this. Surely when we start this now, it should find it immediately. Yeah, here we have it. Stupid me. So keep in mind, when you use these templates, that you always check which operation mode or which mode of columnar transposition cipher you use. As I said, now it works instantly. So this is yes, it finds the correct text after 1 second. Clearly the examples I have shown you here are very short, so we have only key length 9, but let's reopen this template here with the hill climbing, and then we have the test text here, also very short text, but this is with key length of 25. And let's see how long it takes to solve a columnar transposition cipher with a key length of 25. 3 seconds. These algorithms are just amazing and very, very powerful. So with hill climbing, you solve with a ciphertext of length 250 with a key length of 25 in about, what did I say, 3 to 5 seconds. And of course, when you don't know which key length you have, but you know it's a columnar transposition cipher, you could just start it by key length 2 and then let it run until key length 50. And even if it costs you, or if it takes you 2-3 hours, just go away. And when you come back, it probably solved your columnar transposition cipher. Finally, let's have a look also at the crypt search. So we have here the crypt analysis. We put our text also into that. And then we need a crypt. And the crypt is a part of known plaintext. So let's go back to our text. And then let's use the start. This is a test text as a crypt. This is a test text. And we know that our key length, our maximum key length is 9. Oops. Now let's start it and let's see what happens. Okay, it doesn't do anything. Maximum key length for this is a test text. Maybe we need some more. This is a test text, which crypt of length 20. Yeah, then it works. When we have a crypt that is long enough, it can easily compute your key. So I gave it a crypt of length 20. Let's test how long the crypt has to be for this example. I remove 2 letters. It still works. 17? Okay. Our algorithm obviously needs for this text here a minimum length of 18. So for a ciphertext of length 182, it needs minimum length of 18 character crypt, for instance the beginning here, to successfully break this ciphertext here. Yeah, and this is everything that I wanted to show you in this video. I first showed you how the transposition cipher worked and how it works in Crypto2. Then we had a look at the cryptanalysis using the genetic attack. Then we had a look at the cryptanalysis using hill climbing. And that's wrong. This here was brute force, this was a genetic attack, and this here was hill climbing. And finally, we also had a look at how to break a columnar transposition cipher encrypted text using encrypt. Yeah, and as I said, this is everything I wanted to show you in this short video. I hope you like it. If yes, please give a thumbs up. Also, if you did not yet subscribe to this channel and you're interested in more stuff like this, then I highly suggest that you subscribe to this channel. This really helps us to grow the channel and to make Crypto2 more popular. Which is what also very important is that you hit the bell icon to be informed when I upload new videos about cryptography and cryptanalysis. Yeah, and as I said, this is everything I wanted to show you. Thank you very much for watching and see you in the next video.